Hello everyone, I'm Komal Pandey,
And I am Harshita Bagwe.
and today we will be presenting our project on the topic Image Quality Analysis and Grading System. This project is based on research concepts studied in digital signal and image processing, particularly in the area of no reference image quality assessment, where intrinsic image features are analyzed to model human visual perception and generate objective quality metrics.
Problem statement. With the rapid growth of digital photography and smartphone usage, the number of images generated every day has increased tremendously. These images are widely used in applications such as medical imaging, surveillance system, social media platforms, digital cameras, and e-commerce websites. Traditionally, image quality is evaluated manually by human observers. However, manual evaluation has limitations. It's subjective. Different people may judge the same image differently. It's inconsistent. Results vary based on human perception. It's time consuming, not suitable for large data sets. Most traditional image quality assessment methods are fully reference methods, meaning they require an original reference image for comparison. However, in real world scenarios, the original reference image is often unavailable. Therefore, there is a strong need to develop an automated no reference image quality assessment system that can evaluate and classify images independently without requiring a reference image. This project focuses on designing such a system that can automatically analyze the images and classify them into different quality grades efficiently and accurately.
The primary objective of this project is to design and implement an automated no reference image quality grading system. Specifically, our system extracts multiple quality metrics from an image, analyzes technical score, evaluates aesthetic score, computes a sharpness metric, classifies the image into quality grades excellent, medium, or poor. We also ensure that the system can process multiple images in batch mode, making it scalable and practical for real world usage. The idea is to convert subjective image quality perception into measurable quantitative metrics and then apply threshold based classification to produce a final grade.
Proposed methodology. This system follows a structured and systematic methodology. First, image input. First, we load multiple test images and from local storage. In our implementation, we have used 3 to 5 images representing high quality, medium quality, and poor quality. This helps in testing and validating the classification logic. Second, quality evaluation function. Next, we use the evaluate photo quality function to analyze each image. The function extracts several features, perceptual and technical metrics, including first, overall confidence, indicates how confident the model is about its evaluation. Second, technical score, measures technical aspects such as noise, exposure, and clarity. Aesthetic score measures visual appeal and composition quality. Sharpness score measures edge clarity and focuses on the level of the image. Threshold based classification. After extracting the metrics, we apply threshold based classification using sharpness score as the primary parameter. The classification rules are if the sharpness is less than 0.75, it's poor quality. If the sharpness is between 0.75 to 0.85, it's medium quality. If the sharpness is greater than or equal to 0.85, it's excellent quality. Sharpness is chosen as the main factor because it plays a crucial role in perceived image quality. Step 4, output display. Finally, the system prints extracted metric value, quality grade, and explanation of the result. The system processes multiple images sequentially, making it scalable and efficient.
Now, I will explain the system architecture of our no reference image quality assessment model. Our system follows a modular pipeline architecture where the output of one stage becomes the input of next stage, ensuring structured and scalable process. The first stage is the image acquisition layer, where multiple images are loaded from the local storage using Python's file handling mechanisms. This enables batch processing and automation. The second stage is the quality evaluation engine. Each image is passed to the evaluate photo quality function from the photo quality analyzer core module internally. This module applies computational photography principles and perceptual image quality metrics to analyze the image without requiring any reference image. The third stage is feature and metric extraction. Here, the system extracts high level quantitative attributes such as overall confidence score, technical quality score, aesthetic quality score, sharpness metric. These metrics numerically represent perceptual characteristics like clarity, exposure balance, noise levels, and tonal distribution. The fourth stage is the decision making stage, where we implement rule based threshold classification based on predefined sharpness intervals. The system maps continuous metric values into discrete quality grades: poor, medium, excellent. Finally, the output layer presents the computed metrics along with the final judgment, making the results interpretable and user friendly.
Image classification. Now I will explain the three image categories we have in this project. First is the excellent quality image. Excellent quality images have high sharpness and clear edge details, proper exposure and balanced brightness, low noise levels, accurate color balance, wide dynamic range. Since the sharpness score is high, as the noise is minimal, the system classifies these images as excellent. Medium quality images. Medium quality images show slight blur or soft edges, acceptable brightness, minor noise, slight loss of fine details. Because the sharpness score falls within a moderate range over here, the system classifies them as medium. Finally, poor quality images. Poor quality images contain heavy blur or motion blur, high noise, poor exposure, significant loss of details. Due to low sharpness and reduced clarity, the system classifies them as poor. The classification system mainly depends on the sharpness metric because blur directly affects visual perception and usability of an image. Now, moving on to the code explanation implementation part. First, we disable all the logins and warnings to keep the output readable and clean. Then we import evaluate photo quality function from the photo quality analyzer library. We define a list of image files that serve as input. These images are then put into a system where the system checks whether each file exists. If found, it skips the if found, it proceeds with the evaluation. If not found, it skips that image. The function returns a dictionary containing multiple image quality metrics. We extract overall confidence, technical score, aesthetic score, sharpness score. Based on the sharpness score, threshold conditions are applied. Less than 0.75, it's poor. Between 0.75 to 0.85, it's medium. Greater than or equal to 0.85, it's excellent. Finally, the system prints the final grade along with the metric explanation. This makes the system fully automated, efficient, and capable of processing multiple images sequentially. The different type of images we just took in the previous slide are the input for this code, and the result of each of the quality images is as shown in the slide. From the highest quality to a medium quality to a poor quality image, with all its key metric and evaluation criteria as stated.
As you can see on the screen, to begin the implementation, I am cloning the photo quality analyzer repository from the GitHub. This repository contains core analyzer module responsible for computing no reference image quality metrics. This library internally uses computer vision and perceptual analysis techniques to evaluate image attributes. On the screen, you can see that I have next installed the dependencies, the required dependencies such as OpenCV for image processing, NumPy for numerical computations, SciPy for scientific operations. These libraries ensure efficient processing and model inference. Google Colab runs on a Linux-based virtual machine. We can use shell commands by prefixing them with an exclamation mark. This ls command helps us verify that the repository has been cloned successfully and allows us to inspect the project structure. Over here on the screen, we can see the internal implementation of the analyzer module. The key function we will be using is evaluate photo quality, which acts as a primary entry point for quality evaluation. Over here, we are creating a custom execution script to automate evaluation process. Firstly, we disable logging and warnings to ensure clean output visualization. Then I import the evaluate photo quality function from the analyzer core module. Then we define a list of multiple image paths to enable batch processing. Over here, we can see that each image I call the evaluate photo quality function. For each image, this function analyzes multiple perceptual and technical attributes of the image and returns a structured dictionary containing scores and explanation. From the returned results, we can extract overall confidence, technical score, aesthetic score, sharpness score. Take a look at this. Here we are implementing threshold-based classification using conditional logic. If sharpness score is below 0.75, the final grade is poor. If sharpness score is below 0.85, final grade is medium, or else it is excellent. This transforms continuous metric values into discrete quality grades, making the system interpretable and user-friendly. On running this command, we are now executing the script to analyze all images in batch mode. We can observe in the first output, that is test.jpg, that the sharpness score is 1, which indicates extremely high accuracy and edge clarity. The technical score is 0.959, aesthetic score is 0.918, both of which are significantly high. Since the sharpness exceeds threshold of 0.85, the image is classified as excellent.
In conclusion, this project successfully demonstrates a no-reference image quality assessment system. The system automatically evaluates image quality, does not require any reference image, uses perceptual and technical metrics, classifies image into excellent, medium, or poor. The implementation is simple, efficient, and suitable for academic research, image filtering systems, photography quality control, automated surveillance analysis.
Although the current system performs rule-based classification using sharpness thresholds, there is a strong potential for enhancement. Instead of relying primarily on a single metric, we can integrate multiple perceptual attributes such as exposure balance, noise levels, color consistency, and dynamic range into a weighted composite scoring model. This would enable more holistic quality evaluation by considering both technical and aesthetic dimensions, simultaneously thereby improving robustness and decision accuracy. Furthermore, the rule-based decision layer can be replaced with a machine learning-driven classification model by training a supervised algorithm on labeled image datasets. The system can learn complex feature interactions and perform adaptive quality prediction. Deploying the solution as a web or mobile application would enable scalable, real-time image quality assessment for practical user-oriented environments. Thank you.
Thank you.